Good day, everyone. So for this video, we'll be doing physics. We'll be looking at Newton's laws to be specific. So by now, you should know that in total there's 4 Newton's laws, which the first one is Newton's first law, Newton's second law, the third law, and the final one is Newton's law of universal gravitation. Right, so without wasting any time, let's get right into it. So just to zoom in, so the first law, Newton's first law of motion, states that an object continues in the state of rest. So these are the key words, right? So the object will continue at the state of rest or move with what? Move with a constant velocity unless it is acted upon an unbalanced net force, right? So just to fix this, so what this is basically telling us in short is that if we are not applying any net force to an object, that object will remain at rest if initially it's at rest, right? Or if it's already moving at a constant velocity and we're not applying any force to that object, then it will continue moving at that constant velocity, right? So now I'm highlighting keywords here, right? Constant velocity, state of rest, right? Unless an unbalanced force is acting on this object, right? So the formula that we know by now is the F net is equals to ma, m being what? M being your mass, and then a being the acceleration. Okay, so now I've highlighted a keyword here, constant velocity. So constant velocity simply means that the velocity is not changing, right? In other words, how we interpret that is we interpret it with our acceleration being equals to 0. So what does this mean? This means that when we're talking about Newton's first law, in this formula of the F net is equals to ma, mass times acceleration, we have to substitute our acceleration to be what? To be 0. And then now when your acceleration is 0, what if essentially happens is your F net will be equals to what? Will be equals to 0, right? Because any number when you multiply it by 0, it just becomes 0, right? So that product would be 0. So when we're talking about the first law, we're talking about a case where the total net force acting on that object is always going to be equals to 0. It's gonna remain at a state of rest, or it will move at a constant velocity. Okay, so what you've noticed, I've placed the Newton's first law with Newton's second law side by side to what? To show you how these two laws are linked. Okay, so let's just jump right into the second law. So the second law states that when a net force is applied to an object of mass, it will what? It will accelerate. Okay, this is another keyword right here. It will accelerate in the direction of the net force, right? And then it goes on, it says that the acceleration is directly proportional to what? To the net force that is applied, and it's inversely proportional to what? To the mass. Okay, so for this definition I've highlighted a few keywords, but the main one that I would like you guys to focus on is it accelerates. Okay, so now what does this mean? Now it means that we have acceleration. Okay, so now unlike our first case, or our first Newton's first law, where our acceleration was 0, now our acceleration is no longer equal to 0, because we are told that this object will accelerate in the direction of the net force. Okay, so now what do we do now? Now it means our formula F net equals to ma. It'll always be like this, right? Because now we're dealing with the case where acceleration is no longer 0. Okay, so this is the main difference. So this is the main takeaway from the two definitions, right? The definition for Newton's second law and the definition for Newton's first law. So for Newton's first law, just to summarize, Newton's first law, our F net is equals to 0, and on Newton's second law, our F net is equals to ma, mass times acceleration, as we have defined this side on our left hand side for the Newton's first law. Okay, so now we're going to look at two examples where we see the demonstration of these two laws. Okay, so for example 1, we're going to see how we apply Newton's first law. So example 1, so for example 1, let's say you have a box lying on a horizontal surface. So this is a 5 kg block or box, and it's lying on a horizontal surface, and let's say there's some friction, or the surface is a rough surface, right, which it will produce friction in turn. So now we apply a force that is 10 newtons. Okay, so now just to give you a statement to guide you, let's say that the statement says the 5 kg block below moves at a constant speed, constant velocity. Okay, so for now we don't even need to know what that constant velocity is. So now we're given a 5 kg block, and then we are told that it's moving at a constant velocity, right? So the first question asks us to draw a free body diagram. So free body diagrams are really important. Even if in a test or an exam you are not told to draw a free body diagram, I would really recommend that you draw your own free body diagram on the side, so that you can identify all the forces that are acting on your box or your object. So the first question asks us to draw a free body diagram. Okay, and then the second one, we are asked to calculate the frictional force. Calculate the frictional force also known as Fk. And finally, you can be asked to calculate, so this would be your third question, calculate mu k. Which is the friction coefficient, the mu k of the surface. Okay, so now that we've noted down all the questions that can be asked regarding this 5 kg block that we have above, let's start solving this question. So first part, draw a free body diagram. So with the free body diagram, you basically take whatever object, if it's a block or a car, whatever, a skateboard, whatever object that may be, we represent it with a dot, right? And then from there you simply just represent all the forces that are acting on this object. So the obvious one, which we should all know, is Fg, which is our gravitational force. In simple terms, this would be our weight. Okay, and then the force opposing Fg is going to be what? It's going to be your normal force, which we represented with Fn. Okay, and now these are all the forces in our horizontal direction. So just to make that a bit smaller so that it can fit in the space we have. Okay, so now we're done with the horizontal with the vertical forces. So now let's look at the horizontal forces. So the obvious one, looking at our diagram here, it's going to be what? It's going to be the force applied. So we can see the force applied, it's applied to the left. So our force applied, sorry, to the right, so it's pointing to the right. So this will be our force applied. And now again, because on the diagram we can see that even though I've represented it with the blue squiggly lines, this represents your friction. And when you have a rough surface, it consequently means that you have friction, and then friction always opposes motion. Okay, so now assuming that our Fa, which is the force applied, is gonna move this 5 kg block to the right, then it means that this frictional force that we can see that will be produced from this rough surface is going to what? It's going to oppose that motion, so meaning it will point to the left. Okay, so the Fk is going to oppose the rightward motion, so our frictional force is going to be, it's going to point to the left. Okay, so this is all the forces that are acting on this 5 kg block. Okay, and another tip would be in the test or an exam, this would be 4 marks. So if you were asked to draw a free body diagram, this question would have been 4 marks. So what does this mean? It means that you get a mark for each force if it's represented correctly. Okay, so this is another tip. So if you see a question saying draw a free body diagram, you see 4 marks, just know that your free body diagram needs to have 4 forces on it. If it's 3 marks, then it's 3 forces. Okay, so moving on to the second question, right? So the second question asks us to calculate the frictional force Fk. Okay, so now Fk, we've identified Fk from our free body diagram. Okay, we can see that it's opposing or it's directly opposite our force applied. Okay, so now where do we start? We start with our formula. Okay, so the formula is F net is equals to ma. Okay, but then we go to the statement again. The statement told us that this 5 kg block, it moves at a constant velocity. Constant velocity, remember we said it's what? We said that this corresponds to acceleration being equals to 0. So now it means what? It means that when we get to our F net is equals to ma, because now we're looking at the horizontal forces, all right, because this is what we're interested in. All right, so we're interested in this force in particular. All right, so our F net now is going to be equals to what? It's going to be equals to 0, because we were told that it's moving at a constant velocity. So our F net is equals to 0, and then that's when we can start substituting our forces. So we have Fa minus Fk, all of this is equals to 0. All right, then all we just need to do is move Fk to the other side. Then we're gonna have Fk is equals to positive force applied. All right, and then we can now substitute values. So in the diagram we were told, it was noted that our force applied is 10 newtons. So now we simply just gonna substitute 10 newtons in the space of Fa. So now what does this mean? It means that the frictional force is equivalent to the force applied, which in turn it would also be equals to 10 newtons. Okay, so I hope that was clear. So now let's move on to the third question. So the third question asked us to calculate the coefficient mu k, the coefficient of friction of the surface. So now here you have to remember the formula for friction, or for mu k, for frictional force, and the formula is Fk is equals to mu k times your normal force. All right, so just a quick check. Do we have Fk? Yes, we do have Fk. We just calculated it from our question 2, and now mu k is what we're looking for, so we're just gonna skip that. Obviously we don't have it. Then the question is, do we have the normal force? Not yet. Okay, so that means we first need to figure out what the normal force is, then we can come back to this formula and start substituting. Okay, so now let's put this to the side for a bit, and now let's calculate Fn. So now we're gonna do what? We're gonna call out our formula once again. F net is equals to 0, but this would be for the y direction. So why am I saying for the y direction? Well, because this is the vertical forces contains one of the one of the variables that we're interested in, which is the normal force. So, and also noting that this box, it's not going up and down, so it's not moving in any vertical direction, so it means that obviously the acceleration would be 0. Hence my F net here, it was equals to 0. So now let's substitute. So Fn minus Fg is equals to 0, and then take Fg to the other side. Therefore Fn is going to be equals to Fg, and Fg we know that it's equals to mg. And then finally our Fn is equals to mg. So m, which is our mass, is 5 kgs, and our g is 9.8. and then when you now multiply that, you will get, just give me a minute, you get 49. You get 49 newtons. Okay, so now we have our Fn. We can come back to this formula once again. Okay, so now we can start substituting. So what the value we got for Fk was 10 newtons. New K is what we're looking for, and Fn we just found it to be 49, and when you divide by 49 on both sides so that these can cancel, you'll get your mu K as I think it's going to be 0. Let me just confirm this. Okay, so you want to get your answer 0.204. okay, so the mu K, it's unitless because it's a ratio, right? But so this would be your final answer. So don't be confused to just end your calculations at this point here, right? You're not done. The question asked you to calculate mu K, so meaning that once you have your Fn, it's important to remember that you still need to complete your calculations and find your mu K. So for this example 1, it was a demonstration on how we apply our first law, which is the Newton's first law. Okay, so continuing to example 2. So example 2, you pretty much have similar case. So I'm just gonna copy this diagram that we have above. So we have a similar diagram where it's a 5 kg block, we have a force applied that's 10 newtons, but now the difference would be in the statement, and it also has friction. So now the statement would say the velocity of the 5 kg block below is increasing. Okay, so which essentially is changing. So the velocity is no longer constant like we had for the first example in example 1. So now, like I said, the first question can be, you need to calculate, you need to draw a free body diagram. Draw a free body diagram, and follow up to that, can still be asked to calculate the frictional force and finally you can be asked to calculate the acceleration. Of this block. Acceleration, okay, of the 5 kg block. Okay, so now it's a 3-part question. Free body diagram, we need the frictional force, and finally we need to calculate the acceleration. So again, the free body diagram is pretty simple. Like we're gonna have Fg going downwards, Fn opposite to that, and then we have acceleration, force applied. Let me just put these straight. Force applied, and then you have frictional force. Okay, so we've gone over this, so it's not an issue. So now getting to the second part, we are asked to calculate the frictional force. Okay, so for the frictional force, the approach won't be the same as in example 1. Why? Because now when you do Fnet, the net force in the x direction, you no longer have acceleration being equals to 0, and then you just have your force applied and the frictional force. All right, now we're dealing with what? We're dealing with Newton's second law, because as I've said that the velocity is changing. So meaning what they're trying to tell you here is your acceleration, it's no longer equal to 0. Okay, so our Fnet will no longer be equals to 0 like we had at the top. Okay, it's equals to ma, so it's some value which we don't know yet. Hence in question 3 you are asked to calculate what? To calculate the acceleration. So now what would be the approach? the approach would be, and I just realized here I was supposed to provide some more information regarding the mu k. So mu k here, let's say it's 0.2. So the approach we're gonna take, we're gonna first do, we have to find the normal force. Alright, so this is F net in the y direction, right? So in this case it's 0 because, like I've said, our block is not going in the vertical direction, so it's not going up and down, so we don't have any acceleration here, so acceleration will be 0 in that direction. So this helps us to what? This is gonna help us to find the normal force. This will be equals to 0, therefore your normal force equals to Fg, and this is equals to mg. Okay, all right, so now substituting, we have 5, which is our mass, times 9.8, and as we know by now that it's going to give us 49. This is our Fn, the normal force. Then Fk, since we're looking for frictional force, it's equals to mu k times the normal force. Mu k will be given as 0.2, and the normal force was 49. So when you now multiply the two, you should get 9.8 newtons. Okay, so this is the approach now, right? This is a little bit different with how we approached this question in question 1, in example 1, because like I've said, now we are applying Newton's second law, right? Since we were given the hint up there, right, where the velocity is changing, so it's no longer F net is equals to 0. So this is where in question 3, when we're calculating the acceleration, this is where it's going to be clear. So now, how do we calculate the acceleration of the 5 kg block? So now F net, again for the x direction, it's going to, or horizontal direction, it's going to be equals to ma. Okay, so now we no longer equate it to 0 because the acceleration is no longer 0. So now, and we're looking for this acceleration. So now let's go back to our free body diagram. The free body diagram, we have Fk and Fa in the horizontal direction. Okay, so now it means that the force applied minus frictional force is going to be equals to mass times acceleration. And then good thing is we have already found our Fk, and in our force applied, it's given in the statement, in the diagram I mean. So force applied, it's 10 minus 9.8 Our mass is 5 kgs, and then acceleration is what we're looking for. Therefore, we're just gonna divide both sides by 5 so that this can cancel out, and then 10 minus 9.8 divide by 5. This gives you an acceleration of 0.04, and remember SI units for acceleration is meters per second squared. Okay, so this is Newton's second law in action, okay, where we are told that if a net force is applied to an object, the object will accelerate in the direction of that net force. Okay, so the key word there is accelerate, and as you can see, the acceleration is, it has some value. It's little, but it's some value to move the object. Okay, so now we're gonna move on to the last two laws, which is Newton's third law of motion and Newton's law of universal gravitation. Newton's law of universal gravitation. Okay, so the third law is pretty straightforward. It says that when object A exerts a force on object B, what's gonna happen is object B will simultaneously exert an oppositely directed force. Okay, so this is important, an oppositely directed force of equal magnitude on object A. Okay, so just to give you a demonstration of what we're talking about, let's say you have two blocks. Okay, so this would be block A, and then this is block B. These two blocks collide with one another. All right, so once they collide, what this third law is simply saying is force, what we're gonna see is force A on B, and we'll have force B on block A. Right, so these two forces are equal. So force A on B is equal to force B on A, but again they said oppositely directed force. So now they're not just equal, but they have to be opposite. Okay, so we're gonna put a negative there. So this negative is obviously to show that these forces, as you can see, this force is the force A on B is pointing to the right, and then force B on A is pointing to the left. So they are opposite, but they are equal in magnitude. Right, that's something to note. Okay, so now let's move on to the law of universal gravitation. Okay, so in this law it states that every particle in the universe attracts every other particle with a force directly proportional to the product of their masses, and it's inversely proportional to the what? This is important, to the square distance between their centers. Okay, so we're gonna dive in a little bit into this when we look at an example. So now what we need to note is this law has its own dedicated formula, which is the force of attraction is equals to G, which is the universal gravitational constant, and then we have mass 1 and mass 2. All of it is equals to, all of it is over r squared, which this r squared is the distance between the center of M1 and M2. So I'm just gonna label them now quickly so that we are on the same page. So the F you see here is the force of attraction. And like I've noted, the R that you see here, the distance between the center of mass 1 and mass 2, and the G, which is a constant. This is a value that you find in the formula sheet. It's always given. So this is the universal gravitational constant. Right, so now, and just to give you the magnitude for this G, it's 6.67 times 10 to the minus 11. And lastly, these are the two masses that will be attracting one another. Okay, right, so now that we have an understanding of what we're talking about, I would like us to move on to another part or subsection of this universal gravitational law, which is the gravitational acceleration. Okay, so sorry about that. Gravitational acceleration. So this also has its own formula, which is the small g is going to equal again the gravitational constant, and then we have a big M over r squared. Right, so this big M here is the mass of a planet. So if we're trying to determine the gravitational acceleration for Earth, this will be the mass of Earth. If we're trying to determine the gravitational acceleration of Mars, it would be the mass of Mars. Okay, so talking about the gravitational acceleration, so this is the formula for calculating the g, the small g, the gravitational acceleration. So one thing to note is the big M here is the mass of the planet, right? And then we have the R. So the R is, just to describe it here, is the distance between the object and the planet's center. Okay, so what do I mean? So if, let's say this is our planet here, right, and somewhere here this is the atmosphere, right, the atmosphere, and then right on the trace that I'm doing it with red now, that will be the land that we are located at. So what the R means is, if we have a person situated at this point here, and we have the center of the planet here, the R is simply the distance between where this person is situated up to the center of our planet. So that would be the R. So meaning that if in a case where we have, let's say, I don't know, let's say maybe we have an aeroplane, somewhere in the atmosphere of the planet, right? Then, and we are asked to calculate the gravitational acceleration when the plane is situated at that position, then it means that our R will be from the center of the planet up to where this plane is situated. So this will be our new R. So let's call it R2. Okay, so now obviously the further you move from the center of the Earth or of that planet, the bigger the R value will get, right? So that, I just wanted to clarify that part there. Okay, and obviously the M is always the mass of that planet that we're dealing with, unlike when we were looking at the formula for force of attraction, where we're considering both mass 1 and mass 2. Here we're just considering only one mass, which is that of the planet. Okay, so example 3, we have two planets, planet 1 and planet 2. So we are told that planet 1 has a mass of 8 times 10 to the power 10 kgs, and mass 2 has a mass of 10 times 10 to the power 9 kg, with a distance of 70,000 kilometers. Sorry, 78,000 kilometers. So this will be the distance between the centers, as you can see, the centers of the two planets. Okay, so the distance is 78,000 kilometers. Okay, so now we are asked to calculate the force of attraction. Calculate the force of attraction between the two planets. Okay, so this is simple. We're just gonna call out this formula up here. Okay, so where our F, which is the force of attraction, is equals to big G, which is a constant, mass 1, mass 2, all over r squared. Okay, obviously force of attraction is what we're looking for, and then the big G is a constant, which we were told that it's always going to be 6.67 times 10 to the minus 11, and the mass for mass 1, planet 1, it's 8 times 10 to the power 10, and mass 2 we have 10 times 10 to the power 9 kgs. So the SI units are correct for the masses. Now the distance, our distance always has to be in meters, right? So if you look at the way it's given in our diagram, it's given in kilometers. So we now need to change the kilometers to meters, so meaning that it's going to be 78,000. So when you're changing from kilos to meters, it's going to be 10 to the power 3. Then our value is in meters, and then don't forget the squared. Okay, so now when you press this in your calculator, you'll have your answer as, just give me a minute. So you get an answer of 8.77 times 10 to the power minus 6 newtons. Okay, so that means the force of attraction between the two planets is roughly 8.77 times 10 to the minus 6 newtons. All right, so that is your Newton's law of universal gravitation. Thank you.